Hey, welcome back. I'm happy to say there's no new derivative rules today. Instead, we're going to spend the next two topics looking at some practical applications of the derivative, starting with what we call linear approximation. What we've got here is a graph of e to the x and a graph of the tangent line at the point 0, 1. And our first order of business is to find the equation of that tangent line. To find the equation of a tangent line, I need point and slope. I've already got the point. To find the slope, I need the derivative. The derivative of e to the x is itself e to the x, and the derivative evaluated at 0, e to the 0, is 1. So the equation of my tangent line, y minus 1 equals 1 times x minus 0. Cleaning that up a little bit, I get y equals x plus 1. So if I come up to my graph here, I can label this as y equals x plus 1. So here's what linear approximation is all about. Imagine for a moment that I wanted to calculate e to the 0.3 power. Okay, that would be like finding this point on the graph. But without a calculator, I actually can't compute e to the 0.3 power. What I can do is plug 0.3 into the tangent line from a nearby point. So the idea behind linear approximation is if you want to evaluate a function at a certain point, but you can't, you can make a tangent line at a nearby friendly point and then plug into that instead. And the idea is that those two curves won't be that far apart as long as the point where you made the tangent line is reasonably close. So by plugging into x plus 1 instead of e to the x, I can approximate the value of e to the 0.3 power. And notice the distance between these two is not very much. So the error, the amount that I'm actually missing the true value by, in the big picture is not that big. So when this says use the equation of the tangent line to approximate e to the 0.3 power, it just means take 0.3, plug it into the tangent line instead of e to the x. Because without a calculator, I don't know what e to the 0.3 power is. But I can do y equals x plus 1, plug 0.3 into that, giving me 1.3. So the idea here is that e to the 0.3 is approximately 1.3. And that is linear approximation. Now, we do have a formula for linear approximation, but I want to stress to you that we just did it and we didn't need any new information. If you can find the equation of a tangent line, you can do linear approximation. So this formula, f of x is approximately f of a plus f prime of a times x minus a, is just sort of a shortcut. It's a way to condense all those steps into a shorter process. X is the value that you want to plug in but can't. A is that nearby friendly number where you can find the equation of the tangent line. So in the example that we just did, we would say f of 0.3 is approximately f of 0 plus f prime of 0 times 0.3 minus 0. Well, f of 0, e to the 0, is 1, plus f prime of 0, well, f prime was also e to the x, so f prime of 0 is also 1, times 0.3. 1 plus 0.3 is 1.3. So it's the same process. It's really the same steps. It's just sort of streamlined and put into a single process. So here we go. Let's practice it a few times. Example 1, for the function f of x equals ln x, approximate f of 1.5 using the line tangent to the graph of f at 1. Is your estimate too high or too low? So the idea here is I don't know the natural log of 1.5. But I can make the equation of the tangent line at 1, and since 1 is pretty close to 1.5, if I plug 1.5 into the tangent line, it should be pretty close. So, using my formula from up above, f of 1.5 is approximately f of 1 plus f prime of 1 times 1.5 minus 1. So to calculate f of 1, the natural log of 1 is 0. Plus f prime of 1, the derivative of natural log x is 1 over x. 1 over 1 is 1 times 0.5. So the natural log of 1.5 is approximately 0.5. Is this approximation too high or too low? Well, stop and think about the graph for a second. The graph of natural log x looks like this, and we found the equation of the tangent line at x equals 1. So we found that tangent line right there. See how the tangent line sort of balances on top of the graph? It looks like it's sitting above the graph. So notice, for whatever value of x that you plug in, the tangent line sits above the graph, which means using the tangent line to approximate this graph is going to produce an overestimation. So my approximation of 0.5 is actually a little bit too high. Example 2, use linear approximation to estimate 4.01 squared. Is your estimate too high or too low? So I want you to imagine if my function was f of x equals x squared, and I want to plug in 4.01, but for whatever reason I can't do it, right? So what's a nearby friendly number to 4.01 that's easy to work with? Well, 4. So f of 4.01 is approximately f of 4 plus f prime of 4 times 4.01 minus 4. Well, f of 4 squared is 16, plus f prime of 4, the derivative of x squared is 2x, plug in 4, you get 8, times 0.01. So 16 plus 0.08 is 16.08. So my approximation, 4.01 squared, is approximately 16.08. Is that estimate too high or too low? Again, we're going to refer to the graph. The graph of x squared is, of course, a parabola. And we found the equation of the tangent line at 4. So at 4, is the tangent line sitting above the graph or below the graph? Here I can see the tangent line is below the graph, so my estimate is too low. My estimate is too low because the tangent line sits below the graph. 4.01 squared, I think, is 16.0801, so it's just barely too low. And example 3, g of x is a continuous differentiable function such that g of 3 is negative 8. The graph of g prime of x is shown below. Let's go ahead and label that. This graph is g prime of x. What's the approximate value of g of 2.95? Well, this is an interesting question because I can't plug in 2.95 even if I wanted to because I don't have an equation for g of x. So using linear approximation, I know g of 2.95 is going to be approximately, I guess my nearby friendly value is 3. So g of 3 plus g prime of 3 times 2.95 minus 3. And now we just have to sort of piece this together and plug all the pieces into place. For example, g of 3 was given in the problem to be negative 8 plus g prime of 3 times negative 0.05. Well, this is a little bit tricky because how do I know g prime of 3? I don't know what g prime of x is, but I do have this graph over here. So if I come over and I look at this graph and I go to 3, I can see the value of the graph when x is 3 is negative 2. So by going to that point on the graph, I know that g prime of 3 is negative 2. So I'm going to put a negative 2 right there. So I've got negative 8 plus 0.1 is negative 7.9. So g of 2.95 is approximately negative 7.9. And with your current knowledge that you have right now, we don't know if that's an overestimate or an underestimate. Wait till you're older. Last problem on this relatively short day of notes, 2008 AB number 18. For the function f prime of x equals 2x plus 1, and f of 1 equals 4. What's the approximation for f of 1.2 found by using the line tangent to the graph of f at x equals 1? So pretty clear that they want me to do linear approximation because they asked for an approximation using a tangent line. So using my formula, f of 1.2 is approximately f of 1 plus f prime of 1 times 1.2 minus 1. F of 1 given in the problem to be 4 plus f prime of 1. They gave me f prime of x, 2x plus 1, so just plug 1 into that, get 3 times 0.2. 4 plus 0.6 is 4.6, and my answer is D. So to recap, one of the applications of the derivative is this. If you want to evaluate a function at a certain point, but for whatever reason you can't plug that value in, you can instead find the equation of the tangent line at a nearby friendly value and then plug your value into the tangent line. And the reason why that works, the reason why it's a good approximation, is because if you plug into a nearby point, the tangent line and the graph won't be that far apart. So it's a good approximation for the function that you're looking for. Hope that helps. Thanks for watching.